But one of the beautiful things about Peter is he learns from his mistakes and he shares it with all of us so we can actually grow from this whole thing. And that's really been how the net zero energy movement has been, this process of trying it out, making mistakes, having successes, breaking barriers, and it's been a wonderful evolution that we've seen just in the past 10 years here in Edmonton. And it's really made Edmonton a national leader in terms of net zero energy buildings in the country. So Peter's been designing and building energy efficient houses since the 1970s. His company Habitat Studio is in the habit of building houses with a minimum EnerGuide rating of 86. He's built 50 of those, more than 50 of those so far in Edmonton. Peter has also designed and built 11 net zero energy houses in Edmonton's 5,100 degrees centigrade heating degree climate. Some of them have actually spilled over into the coveted net positive energy category. They're generating more energy than they actually use. Peter's a certified passive house consultant. He's incorporated selective passive house. He'll define passive house for you. Measures in his habitat projects. He serves on the boards of the Net Zero Energy Home Coalition and Passive Buildings Canada and the CHBA Net Zero Council Management Committee. He sees his work as a gift to the well-being of the larger community, which allows him to share the whole process. He humbly acknowledges that it takes a community to really accomplish what needs to be done. This combination of partner building, generosity, transparency, and service has allowed Peter to really advance the net zero energy building movement while bringing to Edmonton the honor of being a national recognized leader in the movement. So please welcome Peter.
Heating, cooling, appliances, everything over the course of the year on site. And so that means that they produce energy in the summer when the sun is shining on the solar panels, and well, all year, most of the year anyway, and in the winter they're drawing it back out of the grid, and the amount that they export and the amount that they import is about the same. And as Rob said, we've done 11 of them so far. These are 7 of the early ones. It's getting hard to cram them all into the slide, so I've kind of stopped. Some of them have not performed at net zero. In fact, more than half of them haven't. But lately, we're on a roll. Starting with this one that we built with the we built with National Resources Canada under their R2000 net zero pilot, is producing a nice surplus. We think we've replicated that. We think we now have the recipe. So it's something like this. It's an R40 wall. Does everybody here know what an R value is? Like when we say R values, anybody? I don't need to explain that. Okay. So the recipe is an R40 wall, double 2x4, R80 roof, R37 frost walls, continuous insulation, about R16 under the basement slab, really good windows, and an air source heat pump and air source heat pump hot water tanks. And we'll talk about that a little bit more. And this is what the annual energy flows look like on that particular house. So the green is the energy production in the warm months. So the December is in the middle. The red is energy consumption, and this one in its first year of operation produced a surplus of about 2.7 megawatt hours, and that's a bit dependent on the weather. That was a nice winter and a nice sunny winter. It's dropped below that, but it's never gone the other direction. And we now have 2 more that are using the same recipe that are net positive. So it's really we're really confident that this is the we've got it now. We can do this pretty much anywhere. So that's just a little bit of bragging. Really, we're here to talk about this project in North Kenora, and Rob was talking about a community. This is a community effort. the number of pieces that came together to make this happen is really quite amazing. So we started with in the neighborhood of North Glenora. It's a vibrant neighborhood. It's across the street. Our site was an old church hall and manse across the street from the school and the sort of big block. So great solar exposure. The neighborhood has got lots of renovation going on. It's a kind of a, property values are going up. There's lots of new houses as well. But the school population was low, and the school was under threat of closure or consolidation with another bigger school somewhere else. So that's what the building started with. It was cinder block construction with basically this sort of clay aggregate that was it was kind of quasi insulation. It was, I guess, a little better than nothing. But we've used it when we've needed lightweight aggregate. So it's really clay popcorn sort of. And 1/2 inch of fiberboard in the roof and 7 furnaces. And so the congregation had 2 problems. One was even with the 7 furnaces, when it was cold, it was uncomfortable, and people are aging, and it's you less tolerance for cold, and they couldn't afford it. And the other thing was that they were looking after a family from Myanmar in the manse, and the family has 5 kids, and they also it's a 3-generation family. The parents live there as well, and they found out through that how desperate the need for housing for large immigrant families is. So they set out to solve 2 problems, and they contacted the Right at Home Housing Society. It's a nonprofit housing society that's been building and operating housing in the inner city for about 40 years, and talked to them about how they could do something together, and they Right at Home engaged us. I had been involved with them years ago. I was at their founding meeting, and in fact, it's through them that I'm a partner in Habitat Studio. Ultimately, that's another story, though. And anyway, so we started to design a project, and we engaged with the community, and there were all the usual concerns like parking and traffic, and there was a little bit of sort of NIMBY pushback, and but the consultation was done really well. The community league president was very, very helpful, and it's a good bunch of people. Like these folks are pretty woke, really, and at the end of the day, we went to council and we also listened. We changed a number of things. They wanted to be sure there was a space for a daycare. That was a big concern in the neighborhood. They also wanted to be sure that the church was on the same corner it had always been on. And, so we listened, we did that, and we responded to the parking and traffic stuff as much as we could. And at the end of the consultation process, the only people in the room at the council hearing were the community league president and the planning chair. And I was blushing. They were so effusive in their praise for the process and the project. And so we had our zoning in 5 minutes, and Scott McKean just about fell off his chair. Like it was, and so this is what came out of it. That's what the building looks like on December the 21st. You can see the shadows are pretty long there, and not a lot of solar power being generated that day. But we ended up with a church with a daycare in the basement. There are 31 kids in the school from our project, and so as soon as the school board heard about that, the school was taken off the list, and that was a great thing. We have 16 families living there, families from the original family from Myanmar is there. We have families from Iraq, from Syria, Sudan, and Ethiopia, and about 100 people altogether. So we tore down the old church by hand, and so that we could reuse the glulam arches. And we saved the decking. That got reused, and the stuff that we didn't reuse is being reprocessed into flooring. There was a massive amount of fir decking there, and we did a few other things as well. So it's a stacked townhouse project. So there are 16 units altogether, 4 or 5 bedroom units, and 12 3-bedroom units. And so the units are stacked on top of each other. The lower units have their bedrooms in the basement, and the upper units have their bedrooms on the 3rd floor. And the access to the upper units is via that bridge that you sort of see in the top. And so the floor plans kind of look like that, with the central stair, which I've got a picture from the outside of. And the units are big. Like they're 4 or 5 bedroom units that are almost 2,000 square feet each. If you count the usual real estate way, the walls are a foot thick, so that kind of adds some square footage right there. But and the family from Myanmar is in one of those, and it's full. They need all that space. In fact, when we originally met some of the families there back in the summer, there was one family looking for 2 units. So the 3-bedroom units are have bigger bedrooms, so that the kids' bedrooms are big enough that you could have 2 in them, and lots of them do. So from the outside, it looks like this. We tried to kind of give this feeling of a pattern of a family of entrances, so that it was oriented to the street and just had a really good residential feel, being a fairly large building. And at the back, we've got this walkway that is access to the upper units, and we tried to kind of widen the stairs in the middle and make a bit of a place that we expect lots of kids are going to hang out and fool around once the snow melts, of course. So this is one of the basement bedrooms. So they're nice and light. We've got 2 kids in that one at least. They've got great big window wells. So I mean, that was something I was a little bit hesitant about. I just thought, whether that would be decent housing to have the bedrooms in the basement, but it seems to be fine. Like, there were some people who had a choice between which one they wanted, who chose the lower one because they didn't want to go up the stairs to the second unit. And by and large, the families are ecstatic. It's kind of humbling. So again, nice bright spaces, good big windows. This is a main floor of a 3-bedroom unit. They're fairly long and thin. We had to make them longish in order to get these big bedrooms in them, and but the space is pretty well used. This is a kitchen of one of the so the 5-bedroom units on the ends, the lower ones are also accessible. So they've got wheelchair ramps and wider doorways and accessible tub or shower and that sort of thing. So and that's why the counter is lowered there. They're not at the moment. There's nobody who's disabled in and making use of that. And this is a view to the other a living room in a 3-bedroom unit, and they look out across the street onto the school and to the park. In the church, we reused the original glulam arches to form the sanctuary space, and we also used the decking but spaced it a little differently with landscape fabric on top of it to improve the acoustics, which seems to have worked, yeah. And then we introduced a skylight over the it's a Presbyterian church, so they don't call it an altar, they call it a table. But to bring down this kind of numinous light, and there was an energy cost to that. There's quite a bit of surface area, but it's all R40, and we have a triple glazed window at the top of it, and it's in the modeling. It seems to be okay. And this is a shot of the daycare. It's also nice and bright, and has turned out to be really popular with the daycare operator. There's a kitchen supporting it, and a couple of snack counters, and it's pretty much full. That's what we did. So why did we build such an energy efficient building? This has got to be affordable housing, and one of the just to part of it is because, like, I'm a one-trick pony. This is how we build our houses, and we've got R40 walls, R80 in the attic, the same recipe essentially that we're using in our single-family housing, and we'll talk a little bit more about whether that makes sense or not. But for the Right at Home Housing Society, they know that they're going to own this property forever. Like, no one is optimistic that we're going to have, any other kind of solution to our housing problem, our affordable housing problem within the foreseeable future. So they have a very long term. They have to think about the cost of ownership of the building, and from the very first buildings, they've always built buildings that are better than the code and that focus on durability, because they know that they're inevitably going to incur all those costs, and the more they can do to control them up front, the better. The other thing is that as a nonprofit, it's easier for them to raise capital dollars than operating dollars. People are more willing to give money to, if they can see where their money is going and drive by it, and than if they think it's going away on monthly bills like energy just through the furnace. So that it's just kind of the opposite of the business case for your typical condo developer, whose best bet is to build the cheapest possible building that looks nice to get a high selling price, and then offload the operating costs and the maintenance on the people who bought the units, and we see all too much of that. So it was really nice to and this phenomenon is not unique to Right at Home. I mean, other nonprofits have got this figured out. And does everybody here know what the passive house approach to building is? Can I just see a show of hands just to get a feel? So it's probably the highest energy efficiency standard in the world. It was built on Canadian work, kind of refined in the mid-90s in Germany, and is now kind of being brought back and being put forward as the way we should build all buildings. And I'm going to talk about that a little bit more, some comparisons and how these buildings relate to that in a minute. But the Passive House US Institute has more units in the nonprofit housing sector than any other building type, for this very same reason, that if you're a professional housing manager and you're looking at the long term, you're going to own it forever, the dollars work to do this kind of energy efficiency. So there's another reason that this is a good choice. So this is yeah, okay. I'm going to just take you through this little graphic that I made up. So there's 2007. That's when we built our first net zero house. This is now, that's 2030, when everybody says we're going to be building nothing but net zero energy buildings, and that's 2050, the time by which we in the Western world better be carbon neutral or we're in big trouble. So every building has to be net zero by then. So far, we've gotten this far. That's how many net zero buildings we've built in the last 10 years or so. And we've got all these other buildings, and we're going to have to start to retrofit them, because 70 or 80% of the buildings we'll be using in 2050 are already built. So it's a pretty massive undertaking, and so just to kind of get an idea of, let it sink in a little bit what that means. A couple years ago, we did a presentation on 2 deep energy retrofits here in Edmonton on single-family houses. And I know there are 1 or 2 others. Edmonton has like 200,000 buildings. It's just massive what we've got to do, and it's not just. And this was a perfect building. This was a building that was easy to do because it was old and it needed lots of work. It needed new siding, new windows, and it was actually bought for that reason. But it was sound, so it was worthwhile to do it, and the dollars made sense on it. Stuart reduced his energy costs on that by 90%. With this deep energy retrofit, and we've got to. But this is kind of what we have to do. And it's so we got to do neighbors of this. And I wish I had a picture of Calgary, because Calgary, the way Calgary's laid out, you can, when you drive through on the Stony Trail, it's like there are billions of houses in Calgary. And you see them all because the hills sort of roll up and show them to you. That was the closest I could get for Edmonton. But so we got to fix those, and they're only like 20 years old. So the windows are not, don't need replacing yet. So, nor probably does the siding. And we got to fix all the old ones, whoops, downtown. And we got to fix these ones that aren't even finished. And, So just to go back to that, and so this is taking you through it. So somehow we're gonna do this. We're gonna start taking the buildings we have built today, and we're gonna start retrofitting them. And there's some kind of hopeful possibilities in that regard. And I'm assuming down here that we're gonna start ramping up net zero buildings really fast, and that from 2030 on, that's all we're building. So we're not going to be adding any more to that. But then somehow we're going to have to fix these ones that we just built and are still building. Like, I have no answers for that. So that all is why we need to build houses like this right now, because we just cannot add to that list. That's too much work already. Yeah. And so now I'll take you through just a little bit about how we put this together and kind of the attention that got put to various details. So we started with, like, we've got thermal bridge-free construction, so there's no places in the entire envelope that are where there's anything but insulation between you and the outside. Like, anytime we've got any sort of structure, there's a few little bits of subfloor and that sort of thing, but for the most part, there's almost no thermal bridging there. And so these footings down here that the dividing walls, the party walls are going to go on, are actually wood boxes with insulation in them. So when we put the insulation under the slab, they'll butt into that, and it'll be completely continuous. The insulation on the floor is going to butt right into this insulation here, and that goes up, gets filled in, and gets continuous with the walls above. So it's pretty much thermal bridge free construction, and you can see here we've got 2 layers of styrofoam under the basement floor. We've got poly, like a poly air barrier in between those 2 layers, so that's sealed. That gets wrapped up the wall here so that it can tie into the other wall poly eventually. So it's continuous airtightness and lots of care and attention on the detail. And we had because we delayed the framer so long, he actually prefabbed the walls in Red Deer, and that worked out quite well. It ended up meaning that he wasn't taking up space on site, and we were able to do other things. But he brought up these, well, it was about 5 truckloads of walls. They add up pretty fast when they're 12 inches thick. And so while we were building away on the church, he was dropping this stuff off and getting ready to, I mean, there's a wall panel there being swung into place. But it's our typical 12-inch double wall. So 2x4 inside, 2x4 outside, and a gusset to hold them together so that the pressure of the styrofoam doesn't. And also we get a lot extra strength. Like this building was built with double 2x4s on 2-foot centers, even on the walls that had 3 stories above them and carried the roof. So it's very, very economical. And our usual fussy poly details, and I'll talk about that a little bit more in a sec here. But the same kind of thing where we back up all of our joints with polyethylene and tape stuff and lots of acoustical sealant, and it's a recipe that's been working very well for us on our single-family houses. We're aiming for an air tightness of 0.6 air changes an hour. So that means every with a blower door on it, which is gives you a negative pressure of 50 pascals, which is about what you get in a 30-kilometer-an-hour wind. Just for feel, we would have only 0.6 air changes of an air change every hour with that fan pressure. Our typical new houses are somewhere between 2 and 4 air changes an hour. Older ones can be up to 10. And that's the biggest single source of heat loss in lots of buildings. Anyways, we're aiming for 0.6. And we tried a couple of new things. And this was a suggestion of the framer. So to reduce the complexity around where the floor is, where the joists were going the other way, we just framed the walls higher and put one on top of the other. And that should have given us an air tightness improvement. It certainly reduced thermal bridging, but we didn't actually, that turned out to be a bit of an Achilles heel. We hit only 0.75, so that was a huge disappointment, like a source of shame. I'm kind of, no, seriously, like it's not that, and there are 2 different air test types actually. In the passive house one being kind of with typical German thoroughness, doesn't allow when you're calculating the volume, when you say air changes per hour, the way you calculate that is you figure out how much air is moving, how many cubic feet per minute, and then you calculate the volume of the building and you divide it, and it tells you how much air, how many times. That's how you get the number of air changes per hour. But they take out the volume of the floor and the volume of the partitions, And so when we tested the Canadian way, we're at I believe, 0.62 air changes an hour, but the passive house way, the way that counts, we were at 0.75. So that was disappointing. And we were a little over on the church as well, so we probably can't certify them. When they were really hard to test because we wanted to test what the building air leakage was, and if we just put a blower door on one unit, we would have any leakage between the units would distort the number. So we did it when we had holes between all the units that we were using for construction anyway, so that we could walk from one to the other without going outside. And we had one blower door on the top units and one on the bottom units. But we had to move on. We had people needing to move in, and so when we got that result, we really didn't have time to go back and do a bunch of additional sealing. We did some additional sealing. It's better than the test, but we were not able to test it again. And on the church, we're a little over there, and we might still be able to get that down. It'll depend on whether we've got the bandwidth. But boy, what a lesson! Like we got, and one of the places where I think we're getting the leaking is actually this spot right here. Like when we went around with a smoke pencil, we could find it leaking there. That would have been easy to seal. Our insulating guy who was doing that sealing didn't understand that, and we, by the time we were testing it, we had flooring in a lot of these places. It was hard to get down there to really do much. We did the best we could to fix that, but what a lesson. Like we get way better results than this on our houses, and we should have gotten a better result here because it's the ratio of external area to floor area is so much higher that it should be easier to hit the target. And in fact, the U.S. Passive House recognizes that, and they make you measure leakage per square foot. So, which at this size of building is about the same, it turns out. But as the buildings get bigger, you have to get them tighter. And there's a couple reasons for wanting that tightness, because any air that's leaking out has got humidity in it. And as it's going out, it's reaching a point in the building where it can be almost as cold as outside. And so as it's traveling out through that crack, it's cooling down, and as it cools, it drops the moisture, and you can get frost, and you can actually get quite a buildup. So it's not just an energy issue; it's a durability issue as well. But we've got a safety margin here with the cellulose, because the cellulose is continuous through the whole thing, and if you get a little bit of moisture in there, a little concentration, it acts like a giant sponge, and it just wicks it throughout the mass where it's pretty much harmless and can diffuse slowly out the rest. Anyway, so we also recycled a bunch of all of the wood in the church actually is reprocessed. We built the front doors from it. We took leftover glulam arches and made that nice welcoming entry canopy, and it was the front doors are like 4 inches thick. They're triple weather stripped. They've got R12 insulation in them. We tried to make passive house doors. That was a kind of a vanity thing, just in a weekend project. But and we're still fiddling with the automatic opener with the 3 layers of weather stripping. It's yeah. So and we for the same reasons that they're worried about long-term costs, and we went to. We were really careful about making the building durable and low maintenance. So the siding is hardy siding, and we've got we use building paper so that it would be vapor open, so any moisture that does get in the wall can dry through it. It's better than Tyvek in that regard. We've got these rain screen battens, so there's an air space behind the siding, so that the walls can dry if they ever get wet from either side. And we're actually doing this on all of our projects now. It's just not that hard, and it's required in BC and on the coast. And then, other little details, we have these timber balconies. We were very careful about how we flash them so that, like, wood will last forever if it can dry. And so we've got no places that can really trap moisture, and when they do get wet, they'll dry quickly and hopefully maintain that. And we did a kind of a cool thing with the balconies here. These are precast concrete planks that we made ourselves, and we made them while we were waiting for the geothermal drilling to happen and some of the other stuff. So we've got our structure, our wear layer, and our waterproofing all in one piece. That's really tough. So I told you we just used our recipe on this building. Was it the right thing to do or not? When you're trying to figure out how much insulation is enough, the way you go about it is to figure out how much it's costing to add more and how many kilowatt hours per year you're saving with that extra money. So you can always reduce that decision to that. And I'll give you an example here. This is some work that National Resources Canada did with a program called, like a database program, Tableau I think it's called, where all these points, every point is a solution that's a cost for an upgrade, and it's got on the bottom it's got how much energy per square meter that building is using. And so obviously you're going to do the cheap ones first and then go up the chain, and it's something that really that drives these kinds of decisions. So for example, this is looking at the cost of the insulation under the basement slab in the church. So we started with R16, and that's where we stopped. But and then we said, because we were kind of academically interested in what it would take to take this building to the International Passive House Standard or the U.S. Passive House Standards, and the two standards are different. The U.S. one is climate specific, and these buildings meet it easily. The international standard we don't meet. But I was interested to know what it would cost us to do that. So just looking at the so we started with R16, and and all these numbers come out of the software that is required for testing passive house compliance. It's called PHPP. It's a humongous Excel spreadsheet. So if we were to go from R16 to R24, that's just another 2 inches. We would go on, the building would go from 28 kilowatt hours per square meter per year down to 24. We would so we'd save a total of about 1,600 kilowatt hours a year, and it would cost us about 3,200 at a cost for that measure of $1.92 per kilowatt hour, which is not bad. That's reasonable. But as we go up, like, we kept dialing it up to try to get to compliance, and we had to go all the way up to R64 under the basement slab to get it to passive house compliance, and the last step was going to cost us $12. So that's and we did that for the whole envelope. So we yeah, this is pretty okay. So this column here is where we started and what it costs to get to the step that we stopped at. So you can see we're in the range of $1.77 for the slab, about $4 for the walls, $2 for the attic, that's always going to be an easy one, and $5.50 on the windows. Windows are expensive. And then to get a good HRV is about, for every kilowatt hour a year it saves, about $4. You've got to do it, so it's not a, and airtightness, we were just going to go there. And you can see I still have my optimistic number in here. And so then we dialed up the specs to get that building compliant to the International Passive House Standard. So we had to go up to, is that right? I think that's a typo. Yeah, it says EPS. I did this a little while ago. Yeah, no, that should say whatever I had on the last page, or the last sheet there. Yeah, no, that is 16 inches. It's insane. Yeah, it's well, the difference between PHPP, one of the differences, and the modeling software we use is that it's a static calculation, and that's not how it works in the ground. HOT 2000, our more commonly used software, actually uses dynamic calculation to do it. But anyway, so then we were upping the basement frost walls to R57. Our walls went up to R72, so we had basically a 20-inch wall, R110 in the attic, certified passive house windows, and they're costing like $23 over the ones that we used. And so you can see these numbers are getting pretty big, and that's really why we didn't do it. And the total savings were not that big. We assumed, optimistically, and I think we could have done it, like building with an inside, with a double wall with a 2x4 chase, we could have gotten it to 0.2 or 0.4. I'm pretty confident of that. So all this, so I looked at this, and so this building, as we built it, is using, the church, as we built it, is using about 28 kilowatt hours per square meter. It meets the U.S. Passive House Standard. It's a darn good building. It's net zero energy. The townhouses with exactly the same envelope are 15.3. Like they're a whisker from passive house compliance. But a square foot of insulation in the townhouse is doing exactly the same job as a square foot of insulation in the church. Like it's stopping just as much cold. So I'm still trying to wrap my head around it. It's kind of, the question is it reasonable to do these buildings on a per square foot basis, or is there another metric? I mean, and so just in case, you're familiar with how much passive house construction is going on in Vancouver, and I thought, because I see it there, and I think this is, it's exciting. And don't get me wrong when I say, I think every passive building that gets built is wonderful. It's just that we need to, this is such a big job, and there's so much of it to do, we need to make sure that every penny we spend is doing as much as it possibly can. But, so I just out of curiosity, I changed the weather file to Vancouver, and it actually gets worse. It's more expensive. And I see Godot here scrunching his brow, and it's because it's just the shape of the curve. You hit the flat spot on the curve faster with fewer degree days. And so I don't know why they're doing it. Like, I'm more power to them. It's great. Anyway, so we did all this energy efficiency stuff, and my mandate was just to design an energy efficient building. There was never any discussion about net zero energy. But looking down the road, I thought we need, like it's just a bad habit. I figured out, I did the energy modeling anyway, and figured out that to get enough room. We were going to need as much room for PV as we could possibly get. So I just drew the roof that way. And somebody said, so what's with that? And I said, well, so it could be net zero someday. And they said, we can do that? And that was all the encouragement I needed. You know, I feel a little bit sleazy about it, but not too bad. So there was no master plan. Like this just, we ran the numbers and we did there was some costing done on the buildings this way with net zero energy. And we did the costing on the building, but somebody did a pro forma on the whole project. And they said the numbers were within range, and they had a donor step up to pay for the PV system, and so it was just full steam ahead. And at that point, we started to look at, this next graph here, or next table. So this is the most modeled building in the world. We modeled it in HOT 2000 to start with. Then we modeled it in PHPP, the passive house software. And then we hired a mechanical engineer who modeled it in IES, which is another one. And it's kind of interesting how close these all are. Like HOT 2000 and PHPP are very, very similar, and IES are very similar, but PHPP shows that we're using, because it's more thorough, it's showing we're using a little more heating. But look at this number here compared with, we use default numbers from Enercan these numbers down here. They're using 50,000 kilowatt hours a year for 16 families. The average Canadian family uses about 8,000 kilowatt hours a year for just lighting and appliances. And on a multifamily, with efficient appliances, you can dial that down to about 5,000. So we use that 80,000 number. That's what Stuart used. They use 50,000, which is the maximum the passive house software will allow you to use. And so the rule is you damn well are not going to heat your house with your TV. Like you're going to somehow get your lighting and appliance loads, and that is not going to turn into house to where in fact with real families with real appliance use, even with energy efficient appliances, that heat is there. And so that heat, that's why so that's why this number is low, that's why their total is low, and that's why this number is higher, because they're not calculating so much waste appliance heat heating the house. So if we add this up for the whole building, we're looking at 205,000 kilowatt hours a year we need for it, but we've only got enough space on the roof for 135,000. So we're not going to be net zero energy if we heat it with just electric baseboard. I mean, these units, the inside units, they're using 1,740 watts when it's minus 30. So that's like a hairdryer and 200-watt light bulbs. And so you're going to put in a big geothermal system for that? Well, it turns out we are. So I mean, that just kind of shows you it's full. Like that's what we ended up doing. That's the amount. We could not get any more on there. And so we did the geothermal system, and it turned out to be, I mean, just really a wonderful thing to do, and actually not as expensive as you would think. So if we had left it with electric baseboard, we would have had to put up another 75, the capacity to put up generate another 75,000 kilowatt hours a year. So at say $2, that's like $150,000 minimum. So instead we put it into the ground and didn't spend that much more. And also it solves a problem, because the elephant in the room here is that we're generating all this electricity spring, summer, and fall, and we're using a lot of it in the winter. And so that's fine when we've got a few buildings. What happens when we have thousands of them? We're going to be wondering how, we're going to be telling utilities we need more capacity in the winter because all these loads used to be met by gas. And then in the summer, we're going to say, we want to sell you electricity. So so the more you can reduce that seasonal imbalance, the better. And the geothermal is great for that because we're getting 3.5 units of heat for every unit of electricity that goes into it. And that was fun. Thomas is here from New Energy. They did that. I'm going to talk about that a little bit more. So the other part of the next biggest number was hot water. These are air source heat pump hot water tanks, and so they basically heat your hot water by cooling your house, which is really, is that what we want to do in January? But when you put it all together in a system, it works. So they cool the. This is in the mechanical room of the church, and it cools the mechanical room down there. But the geothermal system gets that energy back with a coefficient of performance, so 3 units of heat for every unit of electricity. So the whole thing turns out to work really well. We've got these going in single-family houses, and they work great. They really like being in the same room as a freezer. The waste heat from the freezer helps the hot water tank, and the hot water tank means the freezer doesn't have to work so hard. So this is kind of what our schematic, the mechanical room is beautiful. It's like, I don't know if you like those kind of things, but they did a gorgeous job of insulating them, and it's all nicely laid out, and even though I didn't give them a fraction of enough room.
You don't see any flowers in there.
Yeah, okay. But the way it's working in the suite is that because we've got tiny closet-sized mechanical rooms, and the way the system is actually working is so there are 33 holes. The pumping we pump a mixture of water and glycol down in there. The temperature down there is about 6 degrees. Anywhere on the planet, the ground temperature for the first layer of hundreds of feet is about the same as the average annual air temperature, which kind of makes sense. And so we pump down water. It comes back up at 6 degrees. The heat pumps cool it off to what, -5, -10? Huh? So it cools that. The heat pumps cool that water, and the energy, it essentially sucks the heat out of the water to cool it. That's what cooling is, and uses that heat to heat the space. And so we've got one of these little mini heat pumps in each unit, and there's great big pumps that live in the church that circulate the fluid in the ground and through the townhouses. They go underground and come up in the townhouses. So that's a townhouse heat pump. It's way bigger than it really is. This is a hot water tank, and so we've got the return air so this is the fluid circulating in the ground. The heat pump magically makes it hot at the top there, and the fan blows it throughout the suite just like a furnace. But to deal with the air source heat pump hot water tank, we bring the return air through the top of the hot water tank so that cold air gets heated by the heat pump. And then we got this other little innovation here where the mechanical engineer wanted us to ventilate the church and the daycare. They wanted enough capacity. He wanted enough capacity to have the daycare full of kids and the church full at the same time. And we were going to have to add at least one more HRV and one more heat pump to do that. And so we managed to convince him that both spaces would never be occupied at the same time at capacity. And so we've got we've got this ducting system whereby the fresh air can be directed either all to the basement or all in the daycare or all to upstairs. And then after we add oh, I got the wrong slide. Wait a minute. What's going on here? Oh yeah, I know. Okay, this is right. There we go. This is right. Yeah, just so if we apply these coefficients of performance, that's like efficiency. We can see that our total heating was 35,000. We're reducing it to 10,000. The cooling demand is really efficient for cooling. It's trivial. The hot water is being reduced to 17, and the lighting and appliances don't change. And so at the end of the day, we've reduced our 205 down to 128, and it works.
So what was the cost per kilowatt hour for this one?
For what?
For the geothermal?
Well, it was about $3 for the cost and the cost increment to go from an alternate mechanical system. So one of the things that's really interesting about this building, to me anyway, is if you look at what's left for heating, 10,000 kilowatt hours there, 15 or 5 there, so about 16,000 kilowatt hours out of a total 130 is space conditioning. And 85% of the load in this building, or both these buildings, is just lighting and appliances and domestic hot water. So it's like completely flips normal buildings on their head. And it also illustrates that there's kind of a limit. So if we'd have added another layer of units on top of that, we would have increased the lighting and appliance loads and hot water by half, but we wouldn't have changed the roof area at all. And we would have made a small increase in the heating. So it might be a limit at this efficiency of PV in this kind of configuration. So we're going to have to start redefining this and figuring out how we can bring in off-site solar as part of a definition. So actually, this is just the same slide again. I got it figured out. So it was an amazing experience, this whole thing. Like, as I said, there's no master plan. We ended up with the congregation doing the right thing, Right at Home did the right thing, the community did the right thing, the school, the daycare, and the Mennonite Center for Newcomers is helping the families adjust to Canadian life, find jobs, learn English, all that kind of stuff. Like, this is exactly what you want to do. If you're going to invite people to live in Canada, you've got to help them get established to be productive Canadians. And these people are they're crackling. They're really ready to go. This is such a good feeling in that regard. And one of the other things that was interesting about this was the level, like the level of engagement and trust that there was on the project all the way down the line was just amazing. Like, we worked way down the process without any kind of a contract with them, and with pretty sketchy budgeting, and the lawyers in the congregation were tearing their hair out, but the people on the committee, there was just a strong bond of trust. We had this, and that went right through the project. Like, I've never been on a project where we hired New Energy Mechanical, who were totally bought into the project goals. They did the mechanical, both parts of it, the plumbing and the heating, and the electrical. They also did the geothermal, and they also ended up installing the PV, even though our contract was with somebody else. But the amount of and that, like, our guys are pretty cooperative anyway, But this was just another level, I think. Whenever there was a problem, everybody was so constructive, and because of the level of trust between us and the congregation and Right at Home. And so the deal that actually worked out finally, so the congregation made the land available to Right at Home for free, which is how they could do it, like a nominal dollar for 50 years. And in return, Right at Home built the housing and the church and is leasing the church back to the congregation and the daycare and managing both buildings. And so it's just, I feel like I'm totally spoiled. Like whenever a project or a problem arose on the site, like 99% of the time, I felt empowered just to do it. Just, somebody had a suggestion to solve it. Like we didn't have, meetings with like $650 an hour consultants to have to worry about a $50 item or even a $4,000 or $5,000 item. We just kind of knew we had the trust. We knew that if we did the right thing, it would be okay. And I have trouble explaining it. The minister was pretty sure she was pretty sure that there was help coming from somewhere, and anyway, they're over the moon about it. The people who are living there are like, there's a community forming among these people. That's really heartwarming, and it's been the most fun thing I've ever done. So with that, I'd be happy for any comments or questions or anything. Yeah. I'm going to try and answer this, and then I'm going to ask Thomas to correct me. I think that with the drilling equipment, this 75 meters is kind of an optimum depth, that once you start to go deeper than that with that equipment, you're having to pull pipe too much. And I think it's deep enough that you're getting decent performance. And also, like for us, it would have been better to drill them deeper for sure, because the disruption on the site and the cost of trenching those lines together and putting headers and stuff like that is significant. And we ended up, I was tearing my hair out. Like I hadn't done any geo on that scale before, and it took over the whole site. If it rained, it looked like World War I, basically, with the mud and the so deeper and less trenching would have been better, but we worked with Revolve Engineering, and that was their recommendation. They're very cautious, conservative. I think all the like they originally had 34 holes designed, and then we tested the performance of the first hole while we were still drilling, and based on the performance, we were able to drop it to 33.
You said you're using water and glycol,
Yes.
and this is used to collect more heat out of the soil, the ground?
Well, it's just the heat transfer medium.
Yeah, I know.
And the reason for the glycol is that you don't want that water to freeze, because it can be cooled to below zero.
Yeah, okay. But basically you're taking more heat out because you're using glycol from ground.
It's not a very rich mixture.
Here's my question. Is anybody thinking for the far future where you have a whole lot of these types of units close together and you can't put enough heat back into the ground to supply
I'm going to try and answer that. So one of the things that could have reduced the amount of disruption to the site would have been putting the holes close together. And Jacob at Revolve would not let us go any closer than 7 meters on center for exactly the same reason. So these holes have to treat each other in the same way that they would treat a field around them, essentially, or one next door. So you should be able to put an identical one as long as you go 7 meters away and get the same performance.
The interesting
thing about this overall system was that because there's so much energy sharing going on in this building, we've designed the geothermal system to basically be extended from the ground loops all the way throughout both buildings. So what that means is we've got a primary circuit, which is your ground loop, and your secondary circuit, which is circulated throughout the building. That primary circuit is regulated on temperature differential VFDs, so the pumps will regulate based off the amount of energy it needs to draw out of the ground. Now, because the building dynamic of Peter's building, the outside units and the bottom units will be more heating dominant than the center units and the upper units, which will be more cooling dominant. So because each one of these heat pumps exists in that same secondary circuit, some are going to be giving and some are going to be taking. Even in, I think, January, we had a couple of the units in cooling mode because there was that much heat being generated from the internal inhabitants. Like there's, 100 people living in 16 units. Each person gives off a certain amount of heat. Each object
65.
gives off a certain amount of heat. So we're very excited to see what the actual performance will be over the next year, to see that there's actually maybe even a bit of more cooling dominancy than heating dominancy. So again, based off the shared energy loads of these buildings, we're able to go with a bit of a lower temperature demand. So
There shouldn't be, the pipes are polyethylene and they're welded. Like they're fused, and in the, the worst thing for plastic is actually sun. There just ain't a lot down there. Yeah. No, I mean, it should be pretty much permanent. I mean, it's as good as the soldering, really. The cells should last virtually forever. Like, he calls it a rock that makes electricity.
And the batteries?
Well, there are no batteries in the system. We're using the grid as a battery, essentially, so any extra energy we produce gets used by the neighbor's fridge, or wherever the nearest place or Westmount Mall, if it's, yeah. Yes?
Just curious if there is measurement and verification happening for heating and cooling of the units.
If there's
measurement and verification.
So that's something we're very interested in, and we're just finishing off a proposal to Canada Mortgage and Housing, and who have verbally anyway said that they're interested in funding a measurement system. New Energy ran Cat 5 cables from the main electrical room to every suite with the hope that we could find some funding to do that. So I think it'd be very interesting to do in a number of respects. Yeah.
You haven't really, as I see it, addressed the issue of direct gain in terms of passive heating. In terms of explaining, like your overhangs seem a little unconventional. Maybe you could just touch in on that. How much of the heating is really derived from passive heating in this case?
I'd have to go back and look at the model. We know the balconies are cutting off a lot of nice gain on the main floor units, but we had to do them. We're required with stacked townhouses to have that kind of amenity space, and we really didn't want to go to the extra expense of messing with the structure to sort of make the bottom ones even bigger, and it wasn't that far off. So, and then the top units, like we needed a high heel on the truss. We did stick it was kind of the best we could do. But the other thing is, so we're going to get good gain on the top units for sure, and maybe too much, but we can cool very, very cheaply, and it's kind of a compromise. Yeah, and so it's kind of when we first started doing this on like 12 years ago, 10. We were, and PV was costing about $7 for the capacity to generate 1 kilowatt hour a year. I won't even tell you what we paid for this. It was under $2, and I mean, we got a really sweet deal. It was partly a donation, I think. Anyway, when it was $7, we wanted to get every watt of electricity that we could out of every panel that we put up. And so we started off, and we were looking at stuff like solar thermal because we thought it was cheaper. And really big, we went big in passive solar too, to try to keep that heating demand down so that we wouldn't need much, so we could get enough PV at the optimum angle. We were angling, the roofs look, we have one roof that looks exactly the opposite of that. You just take that truss, spin it around. Yeah. Yeah, well, and that was when PV was expensive, and then when the price came down, and we started to make this work on non-perfect sites where there wasn't as much passive solar available, we realized we could make it by just, and some of this is based on a study that Nate did. They actually had they put some solar panels on the building where they put them at varying angles, and they measured the output of all of them, and they swept the snow off one set and not off the other. And what it turned out to be was, it matters. It's better to go on the optimum angle, but it's not a deal breaker. You're better off to have more area. And now it's cheaper to put up more solar panels than it is to put in more insulation. When we were doing that, we had 16-inch thick walls, and now we're going 12-inch. So we dialed back. It's all about that cost per kilowatt hour, whether it's generation or conservation. Kind of dialing that in, it worked better to get more area, put more up, and go back a little bit on the conservation. Yes, right there.
We got a mic back here.
Yeah, no, I can see, yeah.
I was just wondering,
Rob, I was going to answer his question before, but you had the microphone.
I was wondering if you've done cost comparisons between the building you built, the rental units there, compared to commercial units of the same size or numbers, and built to a conventional design or the code.
What's the cost difference?
Yeah.
So the cost difference on the whole project it's a $6 million project. It was about $600,000. So about 10%. Not yet, but we've had a number of inquiries from other churches. There are lots of churches in the same boat. They've got old buildings that are not performing well, and they've got land, and so we're looking at a couple of other. We had a session one day at this church with 6 different people from 6 different congregations, and 2 of them look like they might be serious. So. Oh, sorry.
Great talk, by the way. Amory Lovins of Rocky Mountain Institute was a big proponent of negawatts, using less energy.
Right.
Do you find that, seeing as Canada, I think the U.S. and maybe Australia have probably double the average dwelling as the rest of the world? Like we have about 2,000 square foot.
Yeah.
Whereas the Europeans have about 1,000 square feet. So do you find as buildings are getting more efficient, people don't care about that and are building bigger buildings and using more power? And it seems like it's getting bigger and bigger.
I don't think they're getting bigger anymore. It's getting too expensive to make them bigger now. But I think these people just don't think about it, or they can afford to put up more PV. I mean, it's just not. It's not. Their reckoning of whether they're using their share or more than their share of the planet's resources is not a big motivator. Yes.
Just curious. So, what's underneath the photo panel or the solar panels on the roof? What's the roof finish?
The roof finish is asphalt shingles. Yeah. So that was a cost thing. At one point, we were going to use a metal roof. That roof is entirely covered. Like my hope is that that might need some attention around the edges, but that the shingles in the middle, I mean, it's sun and rain that kill it. These are going to get wet, but they're not going to get any kind of wind, and they're never going to get any sun.
Just wondering if you left an area gap between your panels and your roof, and then if you have any maintenance ways through the panel system.
There's always a gap between, like the racking lifts the panels off the roof. So there's probably a space of, I don't know, how big is the space? Yeah, so Thomas says 6.5 inches.
So most people aren't too aware of thermostats and energy. I've seen houses where people run air conditioners with windows open. Is there anything done here to stop the tenants opening the windows and messing up the energy balance?
Well, I mean, that's a great question. And there was, it's a matter of so these people are from very warm countries. And some of them have been in Canada for a couple of years, some of them just a matter of months. And we definitely need to do some education. Like we've had some units, thermostats turn pretty high. And in one instance, we had, I'll tell you the whole story. Like this woman told me that, and we'd had trouble with the heat pump on that particular unit with one of the main pumps wasn't working at full capacity, and it was the end of the line, and there was inadequate flow there, and it was pretty cold. So we'd fixed it, but she kept saying her kids were cold, and she'd cranked the thermostat higher and higher, and then it got too hot upstairs, and it still wasn't warm enough for them downstairs. So she opened a window, and we also, at one point, to try to get the temperature she wanted, when this heat pump wasn't, she'd gotten a bunch of electric heaters. One of them was sitting right beside the thermostat, so the geothermal system wasn't even working. But she's a smart gal, and she's pretty reasonable. I went over with my little X-ray, spot meter thermometer, and I showed her that the temperature of the basement floor was 26, and she the light went on, and she realized that her kids were not cold. I said, in Canada we use a blanket or a sweater or something. And and it was like and it changed. Like we have had people, probably a consistent problem with the thermostats being set. Like we modeled this at 20, and there were a number of people with thermostats at 26, and so what we're going to do with this monitoring thing is we want to actually work out measure the energy use in each suite, work out a baseline, and relate it back to our modeling, see where it's supposed to be, and then give them an energy budget. And if they use less than that, they get a credit. If they use more, they'll get charged for it. Because we didn't meter every unit. It was way simpler, especially with the solar, not to do that. And the other issue that we've had that we're worried about is block heaters. They don't know what these are. They think they should be plugged in. And so we've had to talk to them about plugging them in at plus 10. So that's, but they're like, when you think about it, if you're living in a spot where there's just total chaos, there's a war going on, and you want to change continents, get as far away from it as you can, and find some place to raise your large family, like that takes resources. These people are not, like they're to the degree that they can speak English, they're articulate, they get it, like you talk to them and they really understand. They're just like us. Like, next year they're going to be here listening. So I'm really optimistic about our ability to do it. Some of them are quite well educated. and have had professions in wherever they came from. They just need a little bit of a boost to get going.
So my question is on passive homes, and I'm real amazed by the innovation and everything that goes into this and all the thought process. But to what degree is considered the building materials inside the home, where the window should be closed all the time for the proper use of the heating and cooling system? But how does that allow for, like say, all the polyethylene and whatnot sheeting inside the home for off-gassing and things like that from new building materials, where they need that time period to give off sort of harmful chemicals and things? Is that all considered in terms of the building material?
Well, kind of wishfully, yeah. I mean, really, there's the ventilation rate. Every unit has an HRV, so it's getting a steady supply of fresh air at about a third of an air change an hour. So that will look after that. If it had been summer, we'd have encouraged people to keep their windows open for the first while. We tried as much as possible to avoid, but we did use a vinyl flooring, and it wasn't my first choice, but on the sort of durability cost thing, it was really what we kind of had to. So it's yeah, I mean, we're hoping the HRV does a good job.
Peter, I want to back to the modules and the snow and the slope. So just 2 or 3 questions. First of all, what's the slope of the roof of the main building and then the church?
The church is about 612, so about 25, 26 degrees, and the main building is 312, so around 15 degrees.
Okay. So then on the main building, you won't have much snow sliding. Is that been the experience? Because do you have any snow dams?
We don't have any snow dams, and I've been kind of watching it this winter. We've almost had no snow step. Like there's something, but most of it's blown off before it's collected. I've been watching it nervously, actually. And fortunately, the sliding off on that side is not a big problem, but sliding off the church is a big problem. And it's sliding down into the exit stairwell from the daycare. So we're actually going to solve the problem by putting up more PV.
Okay.
We're building an awning over that has PV on it. So that's going to go up in the next month or so.
Okay. I've done buildings with metal roofs, and my experience with 212 is a very slow slide, but I just built a building with at 412 with PV, and it's not sliding very easily. But I'm pulling it off because it's only 8 feet off the ground. But,
that's been an issue. We've had to put snow guards in basically all of our metal roofs wherever there's been if it's sort of an unused part of the backyard, we haven't worried about it too much. But anywhere else, if it's over a door or someplace where people are going to be, we always put on snow guards.
Right. My experience so far is that the PV glass, the coefficient of friction is much. It sticks compared to a metal roof. Once a little bit of that module is exposed, it'll pick up a fair amount of heat and start to make a nice slippery snow melt layer in between. But the gaps between the modules it does help a bit. Right. Yeah. Anyhow, because you've entirely filled the roof, you don't have any space for snow to kind of gently come off the roof. So I was curious how you dealt with
feelings.
that.
Like you kind of want that snow to slide off, so that it'll get back to work, but at the same time you don't want it to come down and hurt somebody.
In those cost comparison tables, the column that you had on the left, was that kind of your datum or whatever, was that compared to the net zero house? And then as you were going on, you were going to the passive house? What was that first one that was the...
that was compared to what we built. Like the lowest case that I put in any of those lines was what we built. Okay. Right, yeah.
Okay. And one last thing, you mentioned that you're anticipating by 2030 and then by 2050 that all houses will be built this way. Yeah. For that to happen, it really needs major changes in the building code. Are you seeing that that's where we're going, in your opinion?
So the Pan-Canadian framework is committed to that. 2032. The BC Building Code has already told BC builders that by 2032, net zero ready, like they've brought in something called a step code, where you can, municipalities can adopt any step they want, but those steps start from the current building code and jump in steps to net zero ready as a, and the, just letting everybody know what's coming. Like, why would you build a house that's going to be obsolete in 10 years? It really helps, and it's no shock. You've had 10 years to get ready. I just had some conversations today. We're going to try and encourage Alberta to do the same thing, to introduce BC did a lot of really good work on working this out, and it was a very collaborative process with industry and all stakeholders, and at the end of the day, everybody endorsed it. Everybody wasn't ecstatic, but everybody was signed on. And so if we can do something like that here in Alberta, that would be great. And then if Enercan is looking at this, they haven't actually said that they haven't said the word step code, but if 2 major provinces did it, it would be really compelling just because it makes so much sense. And one of the things that they've done is that they've made it easier for builders to actually model and blower door test their houses than just build the house from a pick list. So as builders do that, they see the benefits of it, and they get more freedom. They can build it however they want as long as they meet these targets. And you get more innovation. It's just a win-win all over the place. Anybody who is against the carbon tax is saying they don't care about their kids' future. It's that simple. Like, we need to keep this government. Anybody who's threatening to take away the carbon tax is not serious about your kids' future. And it's like, this isn't supposed to be political, but we're in deep doo-doo if we, like right now things are happening. This project is really encouraging, and lots of other stuff that's going on. The City of Edmonton is really, at the administration level, are firing on all cylinders. We're going to see some big changes, and Edmonton is aiming at being, they're talking carbon neutrality now in what's going to go to City Council. Like, not, the timetable is in doubt and under discussion, but there's a serious commitment. And for this stuff to happen, we need to fund it with the carbon tax. The carbon tax is a perfect, like, the free market economy is what got us into this mess, with this wonderful, efficient mechanism for allocating resources has made us all, able to consume all this stuff. It's got to get us out of it too, and the only way to do that is the carbon tax.
I've got the mic, so I'm just going to start talking. Hi, Peter. Wonderful talk. Thank you very much. I just wanted to address the conversation of affordable net zero homes. I work with a builder that tries to achieve the affordable aspect, and we do a rear detached home, full net zero, and we can't sell them. We are trying and trying and trying. So I want to challenge you to ask your builders, talk to people, and take the next step to encourage the industry to start building more of these homes.
We're working on it. Yeah.